So the stuff I just told you about, modal dispersion, chromatic dispersion, Rayleigh scattering, are these things within your control to do anything about? Okay. So these are called intrinsic losses, meaning, yes?
Don't, with improvements in being able to make the stuff purer and purer and purer, doesn't that give you some, I mean, you've got a bunch of old stuff that was made 10 years ago at a certain level of purity. Isn't newer stuff purer?
Yeah. The manufacturing techniques that they're using, well, 10 years ago, yeah, we've certainly made improvements since then. And they continue to make improvements. With multi-mode particularly, single mode, the glass composition of single mode hasn't changed much because it hasn't had to, right? They've done some things with single mode fiber that make it less problematic when you bend it, okay? And that's also the technology there is beyond the scope of this discussion, but yeah, they've made improvements in glass and they continue to do so. Okay, so intrinsic loss, stuff you have no control over. Impurities in the glass, modal dispersion, chromatic dispersion, you can't help that, okay? So those are intrinsic losses. Extrinsic losses are things that you have control over, okay? The first one we're going to talk about is called a microbend. Microbends occur in the optical glass when there's some kind of mechanical force applied to it, whether it's stretching or shrinking, whether it gets something dropped on it, it's stepped on, it's damage to the glass that basically changes its geometry slightly. Not necessarily break it, but enough to make it to where modes that pass through there can actually get cast out of the core because you changed the critical angle. Okay. You can't do anything about that once it happens, it's done. Okay. You can't fix that. Sometimes they can be major loss, sometimes they can be minor loss. It just depends on the severity of it. So the key there is protect the fiber. Right? The one that happens the most and the one you have the most control over is called the macro bend. Right? This is where you've actually exceeded the minimum bend radius of a fiber. And when you do that, what happens is the light can't stay within the critical angle and it escapes into the cladding and it's gone. Okay? If you think of it like, like from a railway perspective, if a train has to pass through a curve at a certain speed, the curve has to be a certain radius in order for it to make it without flying off the tracks. It's the same deal. Okay? Light can't stay in the core if the bend is too tight. Okay, so those were the intrinsic and extrinsic losses. Everybody clear on that? All good? Questions? All right. So I want to talk to this. This is specific to one particular transmission rate, 10 gigabit Ethernet. All right. But here's where you can get a feel for what the differences of the fibers actually are in terms of their capabilities. Right. So if I look at the older multi-mode with the larger core, the 62.5 micron core, which we call OM1. If I try to send 10 gig through that using the only light source that it can take, which is an LED, I can go 33 meters, 100 feet or so. Not very far. Okay. If I try to do that through the next higher grade of fiber, which is the 50 micron core, but still the step index, right, the OM2, not laser optimized, using the same LED light source, I can go to about 82 meters, 270 feet or so. So it's better, but it's still not great. If I now use the laser optimized fiber where we've doped that center core to make the mode slow down and scrunch up the light pulse, now the 50 micron OM3, I can go 300 meters using that VCSEL laser. Slightly more expensive light source, but still not as expensive as a single mode laser. But it gives me way more distance in terms of sending that 10 gig signal. If I use the highest grade of multi-mode fiber, which is OM4, which just has better characteristics than the OM3 and is therefore a little more expensive, I can push that distance even a little farther out to 550 meters, okay, using the VCSEL. So you can see that the older grades of fiber, when we get into these higher data rates, become really limited in what they're able to do. Okay? So this has driven a lot of the development of both lasers and the glass itself. Single mode, no question. Okay, I can go 80 kilometers on single mode fiber using a laser and run 10 gig. 80 kilometers. So there's an explanation of the impact of modal dispersion, the source of the laser, and just the characteristics of single mode. Okay? This is precisely why most of single mode is used for long haul and most of multi-mode is used for short stuff. Right?